Hello everyone, welcome to lesson 2.7 on families of functions. My name is Mr. Teal and I'll be taking you through this lesson today. So let's go ahead and take a look at some vocab words first as a little introduction. So if we look at the first point here, today we're going to be looking at families of functions. Now the simplest form and a set of functions that form a family, namely this ugly function right here, is commonly called the parent function. Now, you might have heard this term before, the parent function. We use that term a lot in algebra. Now, if we're looking at the parent function of, for example, a linear function, the parent function of a linear function is going to be the simplest form of a linear function. So I'm going to say parent linear is y equals x. So if you think about straight lines, that is the easiest equation we can think of when it comes to linear functions, right? There are no sorts of transformations done to it, no funky things, no different slopes, no different y-intercepts or anything. This is the simplest form of the function, so we call it the parent function. From here, we can always make different slopes, we can make different y-intercepts if we change the numbers and the order of this function right here, okay? So if we were to put a number in front of this x, that would tell us that we are looking at another slope, a slope that is not 1. If we were to put a number on the outside over here, this would tell us that our y-intercept is different. So we can make changes to that parent function to represent different graphs, but that is the simplest form, so we call it the parent. Looking at point number 2, a change made to at least one of the values a, h, or k, that is going to be called a transformation. So if you are changing something about this graph, so if we're looking at this function up here, if we're changing any one of these values, whether it's the a, so the number out front, whether it's h, the number inside parentheses, or k, the number on the outside, we are making a transformation. Now there are 4 types of transformations. The first type of transformation is a reflection. So this essentially means we're reflecting across an axis. The second type of transformation is called a translation. Oftentimes, I refer to a translation as a shift. So write that in parentheses because I might refer to that as shifts today. Number 3, the third type of transformation is a dilation. We might have seen these in geometry. And the 4th type is a rotation. Okay, these are the 4 types of transformations that we have in mathematics. So if we look down here, a translation, this is the first kind of transformation that we're going to look at specifically today. A translation is a shift in the graph of the parent function horizontally, vertically, or both without changing its shape or orientation. So something to note about translation, this means we are simply moving to the left or the right, up or down. We are not changing anything about the graph other than simply where it lies on the coordinate plane. Okay, so we're not changing the direction of it. We're not changing the slope of it. We are simply looking at the same graph, just shifted right, left, up, or down. Now, if we're looking at a reflection is a flip on the graph of a function across a line, such as the x or the y-axis. So if we're looking at a reflection, that means we're moving all of the points across the axis. We're looking at symmetry, right? And we're changing the direction of the graph essentially, but other than that, it is the same graph with the exception of its flip. All right, moving down here, we have multiplying all y values of a function by the same factor greater than 1 results in a vertical stretch. So if we are multiplying all of those y values of a function by the same factor that is greater than 1, that means we are stretching the graph vertically, and we're going to talk about these a little bit later on. Now, conversely, a vertical compression, or in other words, a vertical shrink, I might refer to that as a shrink today. A vertical shrink, that is going to be a reduction in all y values of a function by the same factor between 0 and 1. And again, we will go over that in a little bit more detail later on today. All right, let's first of all look at some vertical translation. So example number 1, how are the functions y equals 2x and y equals 2x minus 3 related? How are their graphs related? The first thing I'm going to do here is I'm going to go ahead and graph these on my coordinate plane. So I'm going to make y equals 2x. I'm going to make that the purple graph. Then I'm going to make y equals 2x minus 3, the green graph. And what we're going to do after we graph them is we are going to compare them. So let's look at y equals 2x. First of all, I notice that my slope is 2 because the number attached to x is 2. And I also notice that I don't have a plus b value, right? So that means I'm essentially saying plus 0. So my y-intercept, my y-intercept is going to be 0, 0. So I'm going to go ahead and plot 0, 0 first. Then I'm going to use my slope to draw some points. So my slope is 2, so that means I'm rising 2, running 1. So I'm going to go up 2 to the right 1, up 2 to the right 1. Let's go ahead and do 1 reverse, down 2 to the left 1. Okay, so that is the graph of y equals 2x. Now that we've graphed this one, let's go ahead and take a look at the other one so we can compare. So if I have y equals 2x minus 3, the first thing to note about this, my y-intercept is going to be 0, negative 3, or negative 3 on the y-axis. So I'm going to plot a point at negative 3 on the y-axis. Now I'm going to use my slope to go up 2 to the right 1 because my slope is still 2. So I go up 2 to the right 1, up 2 to the right 1, up 2 to the right 1. Let's go ahead and do 1 reverse, down 2 to the left 1. All right, let's connect those dots. And let's take a look and see what is similar about these graphs. So first of all, we're going to talk about how these graphs are similar. So the first thing to notice is that these graphs have the same exact slope. And if two lines have the same exact slope, that means that they are parallel and they will never touch, okay? So let's go ahead and write that down. First thing to write down is these graphs have the same slope, which means they are parallel lines. Okay, now we're going to talk about how these graphs are different. So if we take a look at y equals 2x minus 3 in comparison to y equals 2x, I notice that this graph is lower than the top graph, y equals 2x. All I have done, these are the exact same lines, but all I have done is I have moved it down 3 units. That is the only change that I have made to this graph. So what I'm going to say over here is that we have different y-intercepts. And because we have different y-intercepts, that means we have essentially shifted the graph down 3 units, okay? So I'm going to say y equals 2x minus 3 is a vertical translation or vertical shift down 3 units, okay? So all I have done to the green graph is I have shifted it down 3 units from the purple graph. That is literally the only difference. So that is the transformation that has been made. It is a vertical translation down 3 units. All right, let's go ahead and look at example number 2. So we're going to write the equation for a graph of y equals 3x that is translated up 2 units. So if we take a look at example number 1, as we can see, we had y equals 2x minus 3. This minus 3 right here told us that our y-intercept was 0, negative 3, and that told us that we were shifting down 3 units because this y-intercept was 0. So if we're going negative 3, we have a y-intercept of 0, negative 3. That means that all I have done to the graph is I have shifted it down 3 units. This number on the outside right here tells us our vertical translation. So if it's a negative number, that means we're shifting down. If it's a positive number, that means we're shifting up. But we're looking at the number on the outside. So if we're trying to figure out how do we write an equation that is translated up 2 units, that means we are adding 2 to the outside of the equation. So all we're looking at is y equals 3x plus 2. And that right there is the equation for a graph that is translated up 2 units from y equals 3x. All right, let's go ahead and look at the next page. So we have example number 3. How are the functions y equals x squared and y equals x minus 2 squared related? How are their graphs related? So we have 2 different graphs right here. And the first thing I want you to note about this, these are going to be the graphs of parabolas. So you might remember back to Algebra 1, how we deal with parabolas and equations of parabolas. But the first thing we have here is we have the parent function of the parabola, y equals x squared. This means that our vertex is going to be at 0, 0, right? We're not going to have any sort of vertical stretches or shrinks or anything like that. All we are looking at is the parent function. So I'm going to go ahead and graph this first. So if I have my parent function of a parabola, my vertex is at 0, 0. The little trick that I use for graphing parabolas, you can go to the right one and up one, and then to the right one, up 1, 2, 3. That's how we're going to graph parabolas if we don't have any sort of vertical stretches or shrinks. If we were to have vertical stretches or shrinks, these points would be different. And then we're going to do the same on the other side of the axis. So we're essentially reflecting all of these points. So I'm going to go to the left one, up 1, then to the left one, up 1, 2, 3. That's a little trick that I learned for graphing parabolas. Whatever method you used for graphing parabolas, you are welcome to use that method. When in doubt, you can always draw a table of values, and that's how you can figure out where your points lie on your parabola. Okay, so that's a rough sketch of your parabola here. Now we're going to look at the second parabola, y equals x minus 2 squared. Now, if you remember back to Algebra 1, this number on the inside of the parentheses represents a horizontal translation. So on the inside, we are looking at a horizontal translation. Now, something that's very important to note here, if we have minus 2, that minus sign means we are shifting to the right. If we have a plus sign inside the parentheses, that means we are shifting to the left, however many units it says to shift, okay? So inside the parentheses, we need to think opposite. All right, so if we're looking at that translation inside the parentheses and it's a horizontal translation, we are thinking opposite for signs. Negative means right, positive means left, and that is because if we look at the equation of the parent function, right, and if we look at how we use the formula for translations, it always says x minus h. So that minus sign is going to tell us that this is our translation to the right. Okay, let's go ahead and see if we can graph x minus 2 squared. So this tells you right here that all we're doing is we're shifting to the right 2. So that means our vertex is now going to be 2, 0 instead of 0, 0. So on my graph, I'm going to put my vertex at 2, 0. Excuse me. Then we're going to do to the right one, up 1, to the right one, up 1, 2, 3. Then from that vertex, I'm going to go to the left. So I go left 1, up 1, left 1, up 1, 2, 3. And now I'm going to connect my dots using a smooth curve. All right. So now I can see that these two are the exact same parabolas. The only difference is this one, the blue one, has been shifted to the right. So let's go ahead and take a look at some of the similarities. So the similarity that I notice here is they are both parabolas. Okay, now I'm going to look and see what is different about these two. Well, I notice the only difference between these two graphs is that the blue one has been shifted to the right 2. So I'm going to say y equals x minus 2 squared is a horizontal shift to the right 2. Okay, that is the only thing that has happened here. We have horizontally shifted that graph to the right 2 or horizontally translated it to the right 2. Okay, example number 4, let's write an equation for a problem that has the horizontal translation 5 units left. Okay, so if we're looking at the horizontal translation up here, we see that x minus 2 inside the parentheses tells us we're shifting to the right 2. Now if we're trying to show that we're shifting to the left 5, that means that we are going to have to use a plus sign inside of the parentheses, because once again, we said that plus sign inside the parentheses indicates that we are making a shift to the left. So all we're going to say is y equals x, and I'm going to go ahead and leave some space here. This is the form that it's going to follow. And since I'm shifting to the left 5, I am doing plus 5 inside of the parentheses. And this is going to be the equation for a parabola that is shifted to the left 5. Always thinking opposite when we're looking inside parentheses. I'm going to say think opposite for horizontal. All right, let's go ahead and move to the next part of the lesson. The next part of the lesson, we are talking all about reflection. So let's look at example number 5. A reflection flips the graph of a function across a line, such as the x or y axis. For any function f of x, here are a couple of rules that I want you to follow. I'm going to make this look pretty, just so it stands out. Oh, nice little cloud. I love drawing clouds on my notes. I hope that doesn't bother you. So example number one, or excuse me, criteria number one. So a reflection in the y-axis is f of negative x. So I'm going to go ahead and underline this purple. So if we're looking at a reflection in the y-axis, that means that we are taking f of negative x, or in other words, we are changing the x values. So a reflection in the y-axis changes x values. And that makes sense, right? Because if we were to have a coordinate plane right here, let's say I have a point on the left-hand side of that graph. If I were to reflect this point across the y-axis, that means I would flip it over to this quadrant. And if my new point is in this quadrant, what that means is I have essentially changed my x value from negative to positive. So this is going to change your x's from negative to positive, or vice versa, from positive to negative, okay? Now, the second criteria, if we have a reflection in the x-axis, that means we have negative f of x. So I'm going to say x-axis reflection means we have a negative f of x, which means we are changing the y values from negative to positive, or vice versa. Okay, so once again, if we look at over here at that coordinate, so if I have a point right here in this quadrant, that blue point, if I were to reflect this across the x-axis, that means my new point will be reflected over here across the x-axis. All I have done is I have made my y values, they have gone from positive to negative. So I have changed my y values if I make a reflection across the x-axis. So always follow this criteria when we're looking at reflections. Let's go ahead and go down here to where it says, we have a table and a graph, and we're going to make some reflections. So let's look at f of negative x first. So I'm going to make these two different colors. I'm going to make this one green, and that's also going to be green on my graph. And I'm going to make this one light blue. Okay, so if I'm looking at f of negative x, if we look above here, f of negative x tells us that we are making a reflection across the y-axis. So what we are doing is we are changing the x values from negative to positive, or vice versa. So let's go ahead and look at f of x. So if I have negative 5, 1, if I'm doing a reflection across the y-axis, I am changing this x coordinate from negative to positive. So all I'm going to say here is this is 5, comma 1. And I'm going to go ahead and plot that on my graph. So I have 1, 2, 3, 4, 5, comma 1. Let's look at the second point for the green one. So negative 3, comma 4. Again, I am making a reflection in the y-axis. That means I'm changing my x values from negative to positive, or positive to negative. So this is going to become 3, comma 4. I have just changed the sign of my x coordinate. And that's going to be right here at 1, 2, 3, up 1, 2, 3, 4. Okay, third point, I have negative 2, comma 2. Again, all I'm doing is I'm changing my x value. So this is going to be 2, comma 2. And last but not least, I have 0, comma 3. Since I'm changing my x value sign, 0 is neither negative or positive, so I'm just going to keep it at 0, comma 3. Okay, 0, comma 3 is going to be right up here. So I'm going to go ahead and connect these dots to kind of show what is happening here. So if I connect this dot, it's going to look like this, this, and this. So that is my reflection across the y-axis, and as you can see, all of these points are symmetric, so we have done the correct job. All right, now let's go ahead and we're going to move this, or reflect it, across the x-axis now. So now we're looking at the blue. So I'm going to go ahead and use the criteria up here to reflect all of these points. So if I'm first of all looking at negative 5, comma 1, and I'm trying to reflect this across the x-axis, what I am doing is I am changing my y values now from negative to positive, or vice versa. So if I have negative 5, comma 1, I'm changing my y value because I'm reflecting the x-axis. So this is going to become negative 5, negative 1. Negative 5, negative 1 is 1, 2, 3, 4, 5, right here. Second point, negative 3, comma 4, I'm changing that y value to negative 3, comma negative 4. So right here I have negative 1, 2, 3, negative 1, 2, 3, 4. Third point, negative 2, comma 2, I'm changing that y value, negative 2, comma, negative 2, right here. And last but not least, 0, comma 3, that y value is going to change to 0, negative 3. So now I have made a reflection in the x-axis. So I'm going to connect these points right here. And I have reflected this graph across the x-axis. So that is how you make reflections. Let's look at example number 6. So I have f of x is equal to 2x minus 1. If g of x is a reflection of the f of x in the y-axis, what is the equation? So again, if we are reflecting f of x in the y-axis, okay, y-axis reflections mean we are changing x's, or we are saying f of negative x. So what I'm going to do is I'm going to plug in negative x wherever I see an x, because again, we're reflecting the y-axis, which means we are plugging in f of negative x. So I'm going to go ahead and do this reflection right here. So I'm going to say f of negative x is equal to, so wherever I see an x, I'm going to plug in a negative x, 2 times negative x minus 1. 2 times negative x is negative 2x, so this is going to be equal to negative 2x minus 1. So once again, we have changed that input value to negative x, and g of x is now going to be negative 2x minus 1. Since we said before, that's what we're looking at, g of x here, I'm going to say g of x equals. Okay, looking at the second example. So if h of x is a reflection of f of x in the x-axis, so now we're looking at x-axis reflections, what is the equation? Well, if we look up here, if we're making a reflection in the x-axis, that means we're changing our y values, or in other words, we're saying negative f of x, so we're taking the opposite of whatever f of x is. So since f of x here is 2x minus 1, I'm essentially saying, well, I want negative f of x. So I'm going to change it to the opposite of this. So I'm going to say negative 2x minus 1. So I'm going to distribute that negative to both terms. And I'm going to have negative 2x. And then negative 1 times negative 1 is plus 1. So I'm saying h of x is equal to negative 2x plus 1. And this is my reflection across the x-axis. Okay? So once again, for part A, we're looking at f of negative x. For part B, we're looking at negative f of x. All right, let's go ahead and move to the next page. So example number 7, we are now going to stretch and compress a function. So the table below represents a function f of x. Find the corresponding values. G of x is equal to 2 times f of x and the graph. You guys, this is literally so easy. If we are making a stretch or compression and the rules tell us that we are saying 2 times f of x, all we are doing is we are multiplying this value times 2. Okay, because that's what the directions told us to do up here. So if I'm looking at 2 times f of x here, I am looking at 2 times negative 2. 2 times negative 2 is going to give me negative 4, so g of x is equal to negative 4. Now we're going to do the same exact thing. I do want you to note real quickly, though, I know I said g of x is equal to negative 4. I do want you to note what the x coordinate is, just so that we can easily plot it on the graph. The x coordinate is over here in the left-hand column. So just nice and easy, after you do 2 times f of x, you're just going to plug that in for the y value. Okay, second one, x value is negative 1, f of x is 1. So if we're going to find 2 times f of x, we are essentially saying 2 times 1. And 2 times 1 is going to give us a y value of 2. So our coordinate is going to be negative 1, comma, 2. Okay, looking at the third one, I have 1 for x, 1 for f of x. If I'm looking at 2 times f of x, that's going to be 2 times 1. So that means that my y coordinate is now going to be 2, and my point is going to be 1, comma, 2. So all I'm doing is I'm multiplying those y values by 2 because that's what the directions told me to do. All right, next up, I'm looking at an x value of 2. F of x is equal to negative 3. So what I'm doing here is I'm saying 2 times f of x, or 2 times negative 3. My new point is going to become 2, comma, negative 6. Last but not least, my x coordinate is 3, my y coordinate is 0. I'm saying 2 times f of x, so my new y coordinate is going to be 2 times 0. And I'm going to have still a point of 3, 0, because 2 times 0 is still 0. All right, so let's go ahead and plot these new points, and this is going to be my vertical compression or shrink function. So if I'm looking at -3, -4, that's going to be right here. -3, -1, 2, 3, 4. -1, +2, that's going to be right here. +1, +2, right here. +2, -6, 1, 2, 3, 4, 5, 6. It's going to be down here somewhere. And 3, 0 is right here. So if I connect these dots, I am looking at a graph that looks something like this. And as you can see, all of my points lie above or below those other points, right? So what I have done here, if I'm looking at the original function, I have stretched it vertically. So if I have a positive number that is greater than 1 that I am multiplying f of x by, that means that I am vertically stretching this graph. So what I'm going to say here, this value represents a. So if the absolute value of a is greater than 1, then that means we are vertically stretching. Cool? So this is how we represent our vertical stretch. And we know that this is a vertical stretch because that a value, the absolute value of it, is greater than 1. All right. Example number 8. If h of x is equal to 1/2 of f of x, find the corresponding values in sketch. Let's go ahead and put these down. So once again, just like we did before, we are taking f of x, and now since we're taking half of f of x, we're going to multiply all f of x values by 1/2. Okay, so let's go ahead and look. Our first one, our x coordinate is -3, f of x is -2. Again, we're taking half of f of x, so I have 1/2 times -2. And my new coordinate is going to be x value -3, y value 1/2 times -2, or -1. Second one, if I'm looking at -2, 2, and I am multiplying by 1/2, my scale factor is 1/2 here. I'm going to have 1/2 times 2. 1/2 times 2 is 1, so my new coordinate is -2, 1. Third one, -1, 0. Since I'm looking at f of x of 0, I have 1/2 times 0. My new coordinate is going to be -1. 1/2 times 0 is still 0. Next one, 1, 4. Since my y value is 4, I'm multiplying that by 1/2. 1/2 times 4 is 2, so my point is 1, 2. Last but not least, I am looking at 4, 2. If my y value is 2 here, I'm multiplying 1/2 times 2. My new coordinate is going to be 4, 1/2 times 2 is 1. Okay, let's go ahead and plot these. So if I'm plotting these on the graph, I have -3, -1. That's going to be right here. Then I have -2, up 1. Then I have -1, 0. 1, 2. And 4, 1, 1, 2, 3, 4, up 1. So my new graph is going to look something like this. Now, as you can see, this is a shrink because we have taken this original function and we have shrunk it. And if you notice, our a value here is equal to 1/2. It's a fraction. Up here, our a value was equal to 2. It was a whole number greater than 1. So if our absolute value of a, or that number out front, is less than 1, then we have made a vertical shrink. So this graph right here is a vertical shrink. All right, let's go ahead and look at combining transformations. So if I look at example number 9, the graph of g of x is the graph of f of x equals x, stretched vertically by a factor of 3, and then translated down 2 units. What is the function rule for g of x? So once again, we're going to put all these together. If we have stretched vertically by a factor of 3, that means our a value, or our value out front, is going to be equal to 3. If we have translated down 2 units, that means on the outside, we're going to have -2. We know that f of x is equal to x. This is our parent function. So now we're going to try to account for all of the stretches and the translations. So If I have stretched this vertically by a factor of 3, that means my a value is 3. So I'm going to have g of x is equal to 3x. And again, since I'm translating down 2 units, I'm going to have minus 2 on the outside, so minus 2. So my answer is g of x is equal to 3x minus 2. All right, moving on to the last page here. We have one more example, then we'll have a quick summary. So example number 10, what transformations change the graph of f of x equals x squared to the graph of g of x equals x plus 4 squared minus 3? Well, first of all, let's go ahead and graph these real quick. So if I am looking at the graph of x squared, that is just a regular parabola. So I'm going to graph that in blue. So vertex is 0, 0. I have up 1, right 1, right 1, up 3 right here. And then same on the other side, 2, 3. Okay, so this is my parent function here. And now I'm going to look at my translated function. As we can see here, if we're looking back to what we know from Algebra 1, our vertex is going to be opposite of this and this. So my vertex is going to be -4, comma, -3, right? Opposite HK. So my new vertex is going to be -1, 2, 3, 4, -1, 2, 3. Then I'm going to use the same rule I did before. Right 1, up 1, right 1, up 1, 2, 3. Then over here, left 1, up 1, left 1, up 1, 2, 3. And now I can see my translation. So what transformations have I made? Well, I have transformed this by moving to the left 4 and down 3. So I'm going to say the vertex of the parabola has shifted left 4 and down 3. My vertex is now -4, comma, -3. Okay? And once again, we know this because if we have a number inside parentheses, that number right there is going to tell us we are shifting left 4, because once again, plus means we're moving to the left, minus means we're moving to the right. And this number up here tells us that -3, that means we're shifting down 3. So the number on the outside tells us where we're going up or down. The number on the inside tells us whether we're going left or right. So the vertex of the parabola has shifted left 4, down 3. The new vertex is -4, -3. Let's go over a summary of what we have learned today. So we have learned some vertical shifts, first of all. So if we have y equals f of x plus c, this means we are moving up c units. That number on the outside tells us what our vertical shift is going to be, up. If we have y equals f of x minus c, that means we are moving down c units. So if we were, for example, to have a parent function, I'm going to go ahead and create one over here. If we said y equals x squared was our parent, if we were to look at a vertical shift plus c, this would be, for example, y equals x squared plus 2. And this would be, for example, y equals x squared minus 2. So that's just a real example of what that would look like. So in this case, we would move up 2 units. In this case, we would move down 2 units. Let's look at horizontal shifts. So y equals f times x, or f of x minus c. This means, again, we're thinking opposite if we're inside the parentheses. So if we have minus c, this means we are going to move right c units. We are moving right c units. If we look at f of x plus c, this means we are moving left c units. Always think opposite inside the parentheses. So once again, if our parent function is y equals x squared, if we are moving to the right c units, let's say we're moving to the right 3 units, this would be y equals x minus 3 squared. If we're moving to the left c units, this would be y equals x plus 3 squared. Notice how we're thinking opposite here. This means right 3 units, this means left 3 units. All right, and finally, reflections. So if we're looking at reflections, y equals negative f of x. So if we're making that reflection, we are saying this is moving across the x-axis. Okay, so I'm going to say across x-axis. And if I have f of negative x, that means I'm moving across my y-axis. So if I am looking at this in a real life example, if I'm making a reflection across the x-axis, I'm going to have y equals negative x squared. And then if I'm moving across the y-axis, I'm going to have y equals negative x squared. The negative x is inside the parentheses if I'm making the y-axis reflection, because all of my x values will change. Last but not least, let's look at some non-rigid transformation that distort the shape of the graph. So if I have y equals c times f of x and c is greater than 1, this means I'm making a vertical stretch by c. Okay? So notice how this is going to be outside of the graph here. This one is also outside, so what I'm going to say is this represents all outside transformations, okay? If we're looking at a real example, let's say our parent function is going to be y equals square root of x. This is my parent. And if I am making a vertical stretch by c, and again, c is going to be a positive number that is not a fraction, what that is going to be is y equals, for example, 2 square root x. That's an example of a vertical stretch. Now, if I have y equals c times f of x, and c is between 0 and 1, what that is telling us is that we are now going to be making a vertical shrink by c. So if that number is a fraction, that means we're making a vertical shrink by c. And an example of this would be y equals 1/2 times the square root of x. All right. Last couple ones. So if we have y equals f times c, or f of c times x, and c is greater than 1, this, instead of vertical, this is going to be a horizontal shrink by 1 over c. We didn't go over any examples of this today, but we will see examples of this later on. If we are looking at something inside the parentheses, so if our scale factor is inside the parentheses right here, that tells us that we are making a horizontal shrink by 1 over c if c is greater than 1. So for example, you might see y equals the square root of 2x. And if, again, we are inside parentheses, we're thinking opposite than if we're outside of parentheses, just like we did up here. So if we are inside of the parentheses and that c value is inside and it's greater than 1, that means we're shrinking by 1 over c. Now, conversely, if that c value is inside the parentheses and it's between 0 and 1, so it's a fraction, that means we are making a horizontal stretch by 1 over c. So for example, we might see a function that is y equals the square root of 1/2 x, and this means that we are actually stretching it horizontally. So we're thinking opposite. Once again, these are going to be represented inside the parentheses. So always looking to see where that c value is. That's going to tell you where we're stretching, where we're shrinking, and what we're stretching or shrinking by. All right, and that is lesson 2.7, and we will see you back here next time.